Welcome back, everyone. This is lecture number 7, and we are going to part 1, obviously, and we are going to talk about Heron of Alexandria. This is one of the last characters for classic mathematics, and we'll talk about Heron's formula for area of a triangle. So that would be Heron's formula for area of triangle. You might say, why do we bother with another formula for the area of a triangle? We already have one, and that is quite nice. Why do we actually need another formula for finding the area of a triangle? Heron's formula is specifically convenient because it allows you to find the area without having to actually know the height. For example, if you have some triangle with known sides, let's say you have this triangle here, and let's say that the sides are 10, 7, and 23. So triangle ABC. Sure, you can find the area of this triangle, but you don't really know the height. So even though you might actually draw the height of this triangle, you don't exactly know, at this point in time, you don't exactly know what this length will be or what this length will be, and so you can actually use Pythagorean theorem to find the length of h, and from there you can actually determine the area of the triangle. So Heron's formula is specifically for cases like this, and it is very convenient. So I'm going to state first what the great theorem actually says. We are going to talk about some preliminaries that are being used by Heron for the proof of his formula. And then we are going to divide the proof of the theorem into 3 parts, part A, B, and C. Hopefully in this first lecture, or part 1 of lecture 7, we can cover up to and including part B of Heron's proof, but we'll see how we go about it. Anyway, so here's what Heron's formula or theorem actually says. Let me just draw another triangle. Let's say I have a triangle, some arbitrary triangle, doesn't have to be a special triangle in any way. So let's say you have a triangle with sides A, B, and C. Oops, I meant to say C here. So the formula says the following: if K is area of a triangle, or we denote by K area of a triangle, then knowing the sides or the lengths A, B, and C, then the area would be the following quantity: little s times s minus A times s minus B times s minus C, where S is the semi-perimeter of the triangle. Semi-perimeter, what does that mean? S is defined to be as A, the length A, plus the length B, plus the length C over 2. Now, the formula looks a bit strange since it involves a square root and involves this other concept of the semi-perimeter of a triangle, but nonetheless the proof is very, very nice, and we shall go through it. But first, let's talk about the preliminaries. The preliminaries that Heron used were actually known from Euclid, or they were treated in Elements, and I simply will state them, and maybe we'll prove 1 or 2 of them as we need to do so. So the first proposition, so these are the preliminaries. Okay, so proposition 1 that is used is the following: Preposition 1, it tells us the following. The bisectors of angles of a triangle meet at a point that is the center of triangle's inscribed circle. So let me draw the picture first and then I will actually state it. So I'll draw the picture first. Okay. All right, so I'll state the first preposition being used. So the bisectors, so these are the angles. Let's say this is again another triangle ABC, and the proposition is saying that the bisectors of the angles of this triangle, they all meet at the center of the circle that is inscribed in the triangle. So that is the picture. And I'll state it really quick. I'll write it really quick. That's the center. So the bisector of the angles, of a triangle meet at a point that is the center of a circle inscribed in the triangle. Okay, so that's what it looks like. In fact, in Elements, this is proved in Book 4 and is Proposition 4 in Book 4 in the Elements. You can find the proof there. Okay, the second proposition that shall be used, the second proposition that will be used by Heron, or in Heron's proof, it says the following. In a right triangle, the midpoint of the hypotenuse is equidistant from the three vertices of the triangle. So let me just draw the picture first, and then again I'll state it. So let's say I have a right triangle. And the statement, so A, B, C, let me call this point D. The statement says that the midpoint of, in a right triangle, the midpoint of the hypotenuse is equidistant from all three vertices. That means that this distance CD is equal to dB is equal to this distance AD. So I'm not going to connect them yet, as I want to state the proposition first, and then I'll prove this and I'll write it in the proof. So in a right triangle, the midpoint of the hypotenuse, okay, is equidistant from the vertices of the triangle. Okay, so we will prove that. The proof is simple. So the first thing we do, obviously we're letting a right triangle, ABC, and let the A be the right angle. So let triangle ABC be right at the angle A. Okay, so the first thing we do is we are going to bisect. So bisect AC at point K. So it is possible to find the middle of a segment. We know that from before. So let's say that this is the middle of AC. Let me call that K, point K. And from K, I am going to, before I move on, in the statement here, it's not that point D is actually given. We are rather going to construct that point D, which is the midpoint of hypotenuse CB. So it's not necessarily given immediately in the statement. So from K, we are going to drop a perpendicular. We are going to drop a perpendicular to AC. Oops, sorry. Okay. So, and draw KD perpendicular to AC at point K. So this is the point, I mean, this is the time when we mark actually this point D. Okay, and we want to show that the point D is in fact the midpoint of BC along the proof. Okay, is one of the implicit things that we are going to actually prove. So this is saying that we find the midpoint K of AC, and then from there we draw a perpendicular line at to AC, and then whenever that perpendicular cuts the hypotenuse, we're calling that the point D. That's what I'm saying so far. Okay, we want to show that for point D to be equidistant from the vertices ABC, it is the same as showing that DC is equal to DB is equal to DA, or AD is equal to BD is equal to CD. But it doesn't matter. Okay, so that's what we want to show. All right, so we are going to consider the following triangles. Consider triangle KDA, and triangle KCD. So these two triangles, and triangle KCD. Okay. So what can I say about them? They turn out to be congruent triangles. Let's see why. So KA is equal to KC. We made sure of that. That's by construction. Bisect AC at point K means that KA is equal to KC by construction. Okay. Also, angle AKD is equal to angle CKD as equal to right angles. That is also by construction. Okay, and KD certainly is common to both. So this is equal to this. These two angles are equal to one another as right angles, and KD is common to both triangles. So by angle side, triangle KDA is congruent to triangle KCD by side congruence scheme. I'm going to continue here. So the proof will continue here. Okay, so what can I say then? Since these two triangles are congruent, then this implies that what? The line CD is equal to the line AD. So equal sides are looking at equal angles, and so on. So CD must be equal to CD is equal to the line AD. That's by congruence. Okay, and also, what can I say about the angle KAD? Angle KAD. Mark this red. Oops. Angle KAD is equal to KCD is equal to this angle. So KAD is equal to angle KCD. Okay. So far so good. What can I say about angle B? I'm going to investigate now what angle B is equal to. Okay, I'm going to investigate angle B. All right, so let's see. Angle B is equal to what? Well, the sum of the interior angles of a triangle is 180, or as it was said in Greek's time, 2 right angles. So angle B would be 2 right angles, 180 in modern notion, minus the sum of these 2 angles, no? So let's see. Angle B is equal to 2 right angles minus the angle A, the entire angle A, plus the entire angle C. That is by things that were mentioned and proved before. Okay, so that is the same as saying 2 right angles. Well, angle A, the entire angle A, by construction is also a right angle. So we're saying 2 right angles, minus A, which is a right angle, minus angle C. Well, that means that angle B is equal to 2 right angles minus 1 right angle is 1 right angle, minus the angle C. Okay. Well, angle C, this entire angle C, is the same as the angle KCD. So I can say that the big angle, well, this angle B is equal to 1 right angle one right angle minus KCD. It's exactly the same angle as just calling that C. KCD. Okay? Well, angle KCD from the step before is equal to the angle KAD. So I'm going to substitute KCD with KAD. So that is equal to one right angle minus KAD. Well, what would be one right angle minus KAD? So I'm saying one right angle minus KAD. So that means the entire right angle A minus that angle red would give me this angle, whatever is the leftover. So the leftover here would be this green part. So I'm saying that angle B is equal to the leftover of the entire right angle minus the red part. So that is equal to the angle DAB, angle DAB. So since angle B, the green one here, is equal to the angle DAB, then triangle DAB is what? Is isosceles. And therefore, what can I say about an isosceles triangle? That would mean that AD is equal to DB. And AD is equal to DB. So we are done because we showed here that CD is equal to AD, then AD equal to DB, and that's exactly what I wanted to show from the very beginning. So we are done with this proposition. So this is proposition 2. Well, proposition 3 used is the following. I'm not going to prove that, but I'm going to state it. Proposition 3. Here's what this is saying. In a right triangle, if a perpendicular is drawn from the right angle to the base, the triangles on each side of it are similar to the whole triangle and to one another. I'll draw a picture, then I'll state it, and then I'll move on. So if I have a right triangle, this is saying the following. So if I have a right triangle, and from the right angle, I draw a perpendicular to the hypotenuse, then these two triangles are similar to one another, and they are also similar to the larger triangle. So actually, let me just do this. So the green and the red are similar to one another, and they're also similar to the larger original triangle. So let me state this. In a right triangle, if perpendicular is drawn from the right angle, to the base, or the hypotenuse to the base. To the base, the triangles on each side of it, the triangles on each side of it, meaning the green and the red, are similar to the large triangle, or to the whole triangle. The whole triangle. And to one another. To one another. Okay. This is actually appears on the 6th book of Elements, and it is their Proposition 8. Okay, so the next proposition, which is also very simple to prove, that would be Proposition 4. Proposition 4. Okay. It says the following. Let me just state it, or first I'll draw the picture so that I can use the space to state it. Okay, so the statement of Proposition 4 is as follows. If ABCD is a quadrilateral, with diagonals AD and BC, with diagonals AD and BC, and 1 and 2 are, so this is angle 1, this is angle 2, and 1 and 2 are right angles, then a circle can be drawn such that it touches all the 4 vertices of this quadrilateral right angles. Then a circle can be drawn passing through the vertices A, B, and C, and D. Can be drawn passing through vertices A, B, C, and D. I'm wondering if I'll use the next page to actually give a proof of this. So that means I'm going to draw this once again. Bear with me for a moment. Okay. So this is lecture 7. page 2, part 1, preposition 4, continues. The proof. Again, before I move on with the proof, let me just draw the picture once again, so I don't have to refer back to the previous page. So this is by construction a right angle, and so is this other one. Okay, I mean, it's managed. So A, B, C, D. This is angle 1, and this is angle 2. Okay, so proof. What we do is the first bisect, let me write the proof here, bisect AB at point M, So let's say that this is the middle of line AB. So then by the previous proposition, M is the midpoint of the common hypotenuse for both of these two right triangles. So is the midpoint of the common hypotenuse for triangle ABD and ABC. For triangle ABC and ABD. Triangle ABC and ABD. They share the same common hypotenuse AB. And M is the midpoint. So by the previous proposition, then and by previous proposition, M would be what? M would be equidistant from both. So let's see. For triangle ABC, M being the midpoint by the previous proposition would be M would be equidistant from A, from B, and from C. Also, for the same reason, for this other triangle ABD, point M would be equidistant from ABD. So that means that AM is equal to MB is equal to MC is equal to MD. All right, I'll write this. M is equidistant from vertices A, B, C, D. So this means that all these full lines, so AM, MD, MC, and MB are all equal to one another. i.e. AM is equal to MB is equal to MC is equal to MD. So that would mean that M is the center of some circle with that same radius. And then we're done. Hence, M is the center of the circle passing through A, B, C, D. Okay. Again, because AM would be equal to MB, would be equal to MC, would be equal to MD, would be equal to the radius of that circle centered at M. So then we're done with this. Such quadrilaterals sometimes are called cyclical quadrilaterals. So this is called cyclic quadrilateral. Be careful not to mix this with the things that we talked about last time, inscribing polygons inside a circle. We were talking about regular polygons last time. This is not necessarily a regular one, so, but they do exist. The cyclic quadrilaterals obviously do exist. Okay, and the last ingredient that shall be used in the proof is Proposition 5. So this is done. Proposition 5, I'm just going to state it, not going to prove it, and then we'll start with part A and B of Heron's proof. Okay, so Proposition 5 states the following. The opposite angles of a cyclic quadrilateral sum to two right angles. So I'm not going to draw a picture because it's the same as this one. So this proposition is saying that the entire angle A plus the entire angle C are equal to 180 degrees or two right angles. I mean, we're not going to say 180 degrees at this point, but I'm just using that as a reference of our modern notion of two right angles. Okay, so let me just state this. The opposite angles of a cyclic quadrilateral sum to two right angles. Sum to two right angles. Okay. All right, very good. This would be the end of part 1 for lecture 7. We'll move on with the next part.